Okay, so particles in different states of matter. Basically, we're talking solid, we're talking liquid, we're talking gas. Okay. Now, the thing you need to know about particles is that the particles themselves, if I just look at one particle of a solid and one particle of a liquid and one particle of a gas, you wouldn't be able to tell the difference between them. Okay? The particles are all exactly the same. The pieces it's made of. It could be individual atoms, it could be molecules if it's a compound. But they're all going to look identical to each other. The difference comes in two things. You're looking for how do they move, and you're looking for how close or far apart they are. Okay, so how could I do that in simple for distribution? Sure. Okay, so if you're talking about a solid, all the particles are going to be crammed together as closely as possible. And it's going to have a definite fixed shape. Okay, so for distribution, they're going to be very close. Now, very common misconception people sometimes have is that particles in the solid don't move. Particles in the solid totally move, but they don't move away from each other. They kind of just sit there and wiggle. Okay, they vibrate. They just kind of sit there and chill and vibrate. Okay. Now, if I want to change something from a solid to a liquid, then what I'm going to do is I'm going to add heat. Conversely, if I want to go the other way, and if I want to change it back from a liquid to a solid, I'm going to subtract heat. Okay? This kind of change, by the way, just kind of a little bonus here, this is a physical change. Okay? State changes from solid to liquid to gas, we are just changing the shape. Like I said, we're not changing the particles, we're not changing the identity. We're just spreading them out or cramming them together. With liquid, if we've got a little more energy, then those particles are going to still be kind of semi-close together. But there's going to be a little more freedom of movement as far as, like, they can slide past each other. And also, you're going to need a container to keep them in, because what they're going to do is they are going to fill that container and take on that container's shape. Okay? So we're going to have slightly more spread out. Now, time out real quick. In most substances, what I'm about to tell you right here is true. Okay, there is one big oddball that's different, and remind me to tell you what the oddball is because it's super important. In most liquids, they're going to be a little more spread out, okay? And they are going to move with a little more energy, okay? More motion, but they still stay close together. But they are allowed to kind of flow past each other. You've heard the word fluid. Okay, fluid comes from the same word we get the word flow from, and it just means particles can slide past each other easily. So particles in a liquid are fluids. Particles in a gas are also fluids. If I then take this and I add even more heat to it, or if I want to come back the other way, I want to subtract heat from it. And then what I'm going to get with my gas particles are going to be moving very quickly in all kinds of random directions, and they are going to tend to bounce off of the inside walls of whatever container they're in. Okay. So we're going to have lots of motion, and they are going to be very spread out. Okay. In fact, the container they're in is going to need to be a container with a lid on it, because if they're not, they're going to escape and they're going to fill up as much possible space as they can. Because they're so spread out, particles in the gas, you can compress them. I can apply pressure to them and I can squeeze them into a tinier space because they've got plenty of space in between them. Okay? Now they're going to go nuts and they're going to start bouncing even faster when I do that. We'll talk about that a lot more in the second semester when we talk about the ideal gas laws. But they can be compressed. Solids and liquids, you can't compress them because they're already as close together as they can get. Now, one more thing I want to mention and then I'll shut up. There's a little boundary right here between solid and liquid. Okay, there's a certain temperature where these properties start changing. And we call this certain temperature right here, depending on what way you go, you either call it melting point. You also call it freezing point. Similarly down here, the point where something goes between a liquid and a gas, we call this boiling point. Coming back the other way, that same temperature right there is called probably, I think, condensation point. And for a certain substance, those temperatures are always going to be the same. Okay? Easiest one to remember is water. For pure water, melting point and freezing point happens at 0 degrees Celsius. For water, boiling point and condensation point happens at 100 degrees Celsius for water. Okay, now that's not going to be the temperatures for any other substance. It just applies to water. Every other substance is going to have its own melting point, its own boiling point. Those are physical properties. Those are also intensive properties because it doesn't matter how much water I have. Water is going to boil at 100. It's going to freeze at 0. I think that's all I have to say. Does anybody have a question?